Okay, starting at section 761, that's on page 76. And it's referring to this figure here, 41. Just continuing a little bit with these different kinds of phase diagrams. The bottom diagram there, that's your standard temperature composition phase diagram for the magnesium silicon system. So, a liquid phase, and you have three stoichiometric solids, the magnesium, the silicon, and a compound Mg2Si congruently melting. Now up above that is a corresponding phase diagram, which is the enthalpy composition diagram. Remember I talked yesterday about corresponding diagrams. I said if you replace one variable, you had these pairs of variables here, which were temperature, pressure, the chemical potentials, and then the corresponding variables would be S minus V, N1, N2. Okay, so now we're replacing temperature. If we replace temperature by entropy, then the diagram opens up this way. Now we're not replacing it by entropy, we're replacing it by enthalpy, but as enthalpy increases, entropy increases. Okay, from the Gibbs-Helmholtz equation, if ds dt is greater than 0, then that implies that dH dt is greater than 0. Or as I said yesterday, you can talk about this being S, you can also talk about H, and you come out almost the same thing. So replacing, it's the same thing. As I replace temperature by entropy, it pulls it. As you go up in temperature, you go up in entropy. As you go up in temperature, you also go up in enthalpy. You can take my word for it that you then end up with a enthalpy composition phase diagram. And this is a phase diagram which obeys exactly the same rules of construction as a three-dimensional isothermal section, if you like. You have one-phase regions, you have two-phase regions with tie lines, and you have three-phase triangles. The red lines on there are isotherms. They're not actually part of the diagram. They indicate the constant temperature lines. The actual phase diagram is the black lines. So over here we have a liquid, and every region here corresponds to a region here. So here you have a liquid plus silicon region, and that corresponds to the liquid plus silicon region here. Here you have a tie line. This red line is a tie line at 1225, and that corresponds to a horizontal tie line over here. In other words, if you take the end of the 1225 tie line on the liquid is here and go vertically up, you're going to end up at that point there. Okay, so, and similarly, every one of these regions here, this two-phase liquid plus compound region is this one here. These tie lines that go across here are these red tie lines here, and so on. And here you have a eutectic in which you have three phases at equilibrium, and that then is a three-phase triangle over here. So like any ternary diagram, any place within the three-phase triangle, you have the three phases at equilibrium. And the three phases have, in this case, enthalpies at the corners of the triangle. Okay, this is an isothermal triangle now, just as this is an isothermal line invariant, this is an isothermal invariant triangle. There's one temperature for this whole thing. So this point here corresponds to, well, you got Mg2Si in silicon, and the liquid composition here for the three-phase region is exactly the same as this region here. Okay, so this diagram then can be, this diagram is a phase diagram, and in fact it is calculated with the same phase diagram algorithm as is used for all the other diagrams in FactSage, and all the lines along here are zero phase fraction lines. So this is a phase diagram built up of zero phase fraction lines, exactly like any other diagram. And the usefulness of this is that you can now do things in this diagram. This would indicate, say you starting off with a, let's say I start up here with a liquid at say 80% silicon. As I cool the liquid, at that temperature you go into the liquid plus silicon region, then you have precipitation of primary silicon with heat being given off. And then at the eutectic reaction you have an invariant reaction at constant temperature while a certain amount of heat, okay, is being given off. And then once the entire eutectic reaction is over, then you cool it down through the two-phase region. This diagram up here now at 80% gives you the heat effect. You're starting off at, let's say, what does that say, 1825. Okay, to go from this point down to the liquidus, that's the amount of heat, that's the sensible heat, the CPDT, the integral of CPDT term. Then this amount of heat from the liquidus point down to the eutectic, this amount of heat here, vertical, is the amount of heat absorbed, or the amount of heat released as the primary silicon is precipitated. Okay, that's it. Okay, so at any temperature you can follow down here as your liquid is going down the liquidus. Then here, now you've reached this point right here. I wish we had a pointer on this rather than this stupid line. You're reaching the point right here on the three-phase region. Now the amount of heat required, the amount of heat absorbed during the eutectic reaction is that distance there from when you're upper boundary to the lower boundary of the triangle. That's the heat. Okay, so this is the sensible heat required, the integral of CPDT to cool the liquid. This is the heat that's given off as you precipitate the primary silicon. This distance is the heat given off. Now, how did I do that? How did I do that? How can I make that a arrow? That is the heat given off as you take off, as the eutectic reaction goes, liquid gives you the two solids, and then here you have the sensible heat to cool. So, okay, now in a binary system, then you got, or to heat it up, it's the same thing. Here I've made an arbitrary zero. This is, to make this useful, rather than putting an absolute heat, I put the heat relative to 25 degrees Celsius, so that this is the heat relative to the heat at 25 degrees Celsius. This is described in a little bit more detail on page 76. These diagrams become useful when you're dealing with ternary systems and so on. Then you can, the binary system, this is fairly straightforward. There was a ternary example given at the beginning of the thing somewhere, which we can, which number was that? Number 3. You might look at figure number 3 and you can see the ternary equivalent of this, and you can see how this can become. Okay, so we kind of invented these diagrams here, and now the phase diagram program calculates these diagrams. So figure 3 is the same thing, but then we've taken an isopleth across a ternary diagram. We've got the enthalpy temperature composition down here. All right, I wanted to go on to, I'm going to skip section 7.7, but for those who love theory, you could read it. Once again, I found a couple of small errors in there, but I don't think it matters. 7.7.1 is the same thing if you're interested in the formal proof of Schreinermaker's rule. But I want to go on to 7.8, which is on the 7.8, which is on page 81. All right, and this is interpreting oxide phase diagrams. Oxide phase diagrams are often presented in different ways, and you can get confused. The main confusion is fundamentally due to the fact that oxygen has iron has two oxidation states, or well, iron's not the only one, but when you have iron, you can have iron 2+, you can have iron 3+, and oxygen pressure then determines the ratio between, and this gets you into all sorts of problems. So let's consider now there are different ways of looking at this, and I'll show you my way of looking at it to try to keep it straight, because you can often get into trouble. And there are different ways of doing it, and I've had discussions with people about what is the best way to do it, but I'm trying to do it in terms of the scheme that I talked about on Tuesday, where we had the table, or you had the temperature, entropy, pressure minus volume, mu1, mu2, and so on, and then you have n1, n2, n3, and you got to choose one variable from each conjugate pair, find the size of the system, take 2 is okay. So I'll try to do it in that case. So here we have, the iron silicon oxygen system, well, I can write it iron silicon oxygen or iron silicon O2, it doesn't matter. This is in terms of the elements, so if you do it in terms of the elements, then you're not going to get into any trouble, but that's not the way people do it. So let's look at figure 43. So there's figure 43. And this figure, it says, this is an isoplethal section across the Fe3O4 SiO2 joint. Alright, now this means then this you have over here, we'll have this point here is Fe3O4 composition, and over here you have SiO2. And what you're doing here then is you are taking the vertical section across this isoplethal joint. Okay, so this is just a standard isopleth. And it is not then a quasi-binary diagram. And this is also, but when you see this in a book, this will say this is the Fe3O4 SiO2 phase diagram. That's how it will be presented. The title of the figure 17, okay, Fe3O4 SiO2 phase diagram at 1 atmosphere total pressure. No, sorry, not a 1 atmosphere, just Fe3O4 SiO2 phase diagram. Okay, the oxygen pressure is not fixed in this diagram. And this is simply an isoplethal section, just like we showed earlier where you had 3 metals, magnesium, aluminum, silicon. You're taking an isoplethal section and you're just cutting across it. And tie lines are not, this is not a, in this case, this is not a, now in certain cases, like remember when we had calcium, oxygen, silica, the calcium silica system would be an actual quasi-binary section because all tie line. In this case, it isn't the case. You can have overall composition here, but the tie lines can be on different ends. This one phase could have more oxygen and the other phase could have less oxygen. This is simply the overall composition. Or in other words, what you could do, you could consider this to be the starting system. What I do is in a container, I start off with Fe3O4, magnetite and SiO2. I mix them in this ratio in a sealed container. I take a sealed container. I take a mixture of Fe3O4 and SiO2 to start at 25 degrees. The container is sealed up and I heat the system up until it reaches temperature and then it'll reach equilibrium. And this is what I'm going to get. Okay, it's simply an isoplethal section. The lever rule, you cannot, from this diagram, you cannot read the, okay, the liquid, for example, is not Fe3O4. The liquid across here at any given point, if you're in the liquid region, the liquid, if you're in the single liquid region, naturally you're at that point because that's what you started with. But when you're in the two-phase region, the liquid is not necessarily, over here, the liquid plus spinel, it is not necessarily anymore exactly Fe3O4. The liquid can contain some iron 2 plus as well. In this case, it's not too far from being quasi-binary, but it certainly isn't exactly. You can see, for example, this is not what a binary phase diagram looks like. Okay, so just as this is simply an isoplethal section across the system. In other systems, you might find that in this case, it's fairly close to quasi-binary. Most of the tie lines lie pretty close to that line, but not exactly. And there's no reason they have to. So when somebody says the Fe3O4 SiO2 diagram, it really isn't exactly the Fe3O4 SiO2 diagram. The liquid over here is not going to be exactly Fe3O4. It can contain some Fe2 plus, whereas the other phase contains one contains a little less iron, the other contains a little more iron. The spinel phase isn't exactly an M3O4, Fe3O4 phase. It can contain excess oxygen. If we now go to this diagram here, okay, oh sorry, let's go back to the, okay, how am I going to define this diagram? Then, so this is on the top of page 82. The top of page 82, this diagram is going to be worked out this way. I define my components this way. You can define the components any way you want. They don't have to be Fe, Si, and O. It can be anything that's independent. So for convenience, I've defined the components as Fe3O4, SiO2, and oxygen. And the phase diagram, so then I pick one from each, I pick one variable from each pair underlined. I can define the size of the system as Fe3O4 plus N silica, which is basically what I put in there to start with. That's what I put in the system to start with, and oxygen. And my phase diagram variables are temperature, pressure, the ratio of silica over Fe3O4 to silica, and the total number of moles of oxygen over Fe3O4 plus silica. Okay, and what I do then is, in the beginning, I set myself on this line by saying that the total number of moles of oxygen over the number of moles of Fe3O4 plus silica is equal to 0. So I keep total pressure constant, I keep this variable constant, and I plot temperature versus this ratio here. So everything is correct. Okay. So that's the isoplethal section, and that's quite straightforward. Then you come to figure figure 44, and this diagram is quite different. In this diagram, okay, it looks the same. See, over here you've plotted the SiO2 they call this the Fe3O4 SiO2 diagram, but it's an isoplethal section. You simply start off with these two things, you put them in a container that's sealed, say with a vacuum up here, and then you heat it up. Some oxygen. Okay, in this diagram, this is called the Fe2O3 SiO2 at constant PO2. Okay, so PO2 is 0.21 bar, so this is the Fe2O3 SiO2 diagram in air. And this is very, very different from isoplethal section. An isoplethal section, I could draw it, I haven't done it, but an isoplethal section would be simply the same thing. I start at Fe2O3 over here, and I draw a line. I start off with Fe2O3 in silica, and I heat the thing up. Okay, what I'm doing now is I'm not doing that. I'm starting off with Fe2O3 and SiO2, say at 25 degrees. I'm fixing an oxygen pressure of 0.21. Okay, and now I'm heating the thing up, so I'm keeping the oxygen pressure constant. Okay, this is very different because now I'm imposing an oxygen pressure on it. Okay, so the oxygen could go in or out of the phase when the thing reaches equilibrium. And now I am not going across this line. What I'm going across is I'm going across a line of constant Fe2O3, of constant PO2. Okay, so in this phase diagram, you can draw a line of PO2 equals constant. And this line here, okay, is a constant, let's see if I can draw this. Okay, so you're going across the line at constant PO2. Okay, this is a constant activity line. In the oxygen, iron, silicon diagram, you can have several lines like this, which are lines of constant oxygen pressure, constant activity of oxygen. And you're going along a line here, along the line of constant PO2. Okay. So even when you're over at this end, you're not really, this end over here is not Fe2O3. The liquid right at this point, if you were right at this point, the liquid is not Fe2O3. Okay, the liquid is whatever you get if you started off with Fe2O3 and put it into oxygen at 1 atmosphere. Okay. If you're in the liquid region here at 0.1 atmosphere, at 0.21 atmospheres, the liquid is whatever the liquid composition happens to be at 0.21 atmospheres. Okay, so this is the misinterpretation. You say over here you've got pure, this is Fe2O3 SiO2 diagram in air, so this point here is clearly pure liquid Fe2O3. It's not. This is the liquid at whatever the liquid composition happens to be, a mixture of FeO and Fe2O3 at 0.21 atmospheres. How do you understand this axis then? I understand this axis this way, that your components in this system are Fe2O3, silicon, oxygen. We would start out with the mixture of Fe2O3 and silica at 25 degrees at whatever ratio we have here, and then we keep the oxygen pressure constant. So the amount of oxygen in the solid and liquid phases will change. Okay, so the system, the solid and liquid phases contain Fe2O3 and SiO2 and oxygen. Okay, the amount of oxygen is not specified, it's determined by the oxygen pressure. Okay. Again, this diagram is not too far, well no, sorry, I'm totally wrong. Also here, you have, in every given phase, here you have spinel plus liquid. You're starting with Fe2O3. Let me, oh well, okay, I'm going along at 0.21. PO2 is 0.21. My two phases, okay, this diagram looks like a binary diagram. It is not a quasi-binary diagram, right? Because it really has three components for sure. Okay, and the phases are not along this composition line. But it has exactly the geometry of a binary phase diagram, and the reason being that when PO2 is constant, all phases have to have the same PO2 at equilibrium. Okay, so necessarily then all tie lines lie on this curve. This curve is not an isopleth, it's not the Fe2O3 SiO2 isopleth, it's a curved line, which is a constant oxygen pressure line. But any overall point on that line, the two phases in equilibrium also have the same oxygen pressure, so they also lie on that line. Okay, so the tie line rule applies. They can apply a tie line across here. That will give me the amount of the liquid phase and the amount of spinel is Fe3O4, not Fe2O3. The spinel is Fe3O4. So here I would have spinel Fe3O4, okay, in equilibrium with a liquid phase at this Fe2O3 SiO2 ratio. Okay, but so and the tie line would apply. The lever rule would apply. But remember now, this end of this tie line does not give me the liquid terms of Fe. It gives me the liquid now contains the three components: Fe2O3, silica, and oxygen. The composition here is going to give me the Fe2O3 silica. The composition on this liquidous thing here is going to give me the ratio of Fe2O3 and silica in the system, but it's not going to tell me how much oxygen is in the liquid phase. You consider the liquid phase consisting of components Fe2O3, silica, and O2. The composition on the liquidous line here, down here, gives me the ratio of silica to Fe2O3 plus silica in the liquid, but it doesn't tell me how much extra oxygen there might be, or how much deficit or excess of oxygen there might be. Okay, now if you want to look at the variables of that diagram in terms of this scheme, so you can see this can get complicated and can be very easily misinterpreted. Okay, so I said here, since PO2 is the same in all phases at equilibrium, the compositions of all phases as well as the overcomposition lie in the constant PO2 line. Hence the figure is the same topology as a binary T composition diagram. All tie lines lie in the plane of the diagram, and the lever will apply. So this is the scheme. I've defined the components as Fe2O3, silica, and oxygen. But whereas now in the previous diagram I chose NO2 as one of the variables, now I choose MuO2. The size of the system is the Fe2O3 and silica that you put into there to start with, and these are the phase diagram variables. So we keep the chemical potential of oxygen constant, and we plot temperature versus the silica to NFe2O3 plus silica ratio.
Sorry, shouldn't it be, I think it's a mistake in the text again. For the P, you have two P's. The
Where?
potential is P, but the other should be minus P.
U minus P.
Yeah.
Q.
Your Q, I should be minus P.
Oh my God. Should be minus V. And it should not be underlined.
Yeah.
I don't know how, this is astounding, you know. Okay, and what I said then is that the phase boundary lines give the ratio of silica over Fe2O plus silica, the individual phases, but they don't give the total composition, which may be deficient in oxygen. Now, the diagram, this is another, that's one way of looking at the diagram. Another way of looking at the diagram is on figure 46. And this is another way of looking at the same diagram. This is the line here at PO2 is 0.21 bar. Okay, so the, as I said here, you're going along this line. Tie lines lie on that line, so if you have a solid here, overall composition here would be in equilibrium with two phases here. Okay. But another way of looking at the diagram is as a projection. You can think about this yourselves. Okay, these are the actual, say this is the line along here, and let's say you have a two-phase region with an overall composition here in equilibrium with this phase and this phase. Another way of looking at it is you draw this Fe2O3 SiO2 straight line joint, you project lines from the oxygen corner of the diagram down to here, straight lines, and this phase diagram along here, then these are the points that you would actually see on the diagram. It's basically a projection. This is the phase diagram along this line, is a projection of the equilibrium points onto the Fe2O3 SiO2 line through the oxygen corner. And that's the way it also is presented, but I find that that's okay. So think about it and convince yourselves that that is equivalent to what I just told you. Okay, you're good. This is the Fe2. These lines come from the oxygen corner are lines of constant ratio of Fe2O3 to silica. Okay, so this is simply giving you the Fe2O3 silica ratio. That's what it is. Okay. So that's another way of looking at the diagram. Then we have figure 45. All right, and this diagram is presented as the, also generally written as the FeO Silica diagram in equilibrium with iron. So this is FeO Silica, this is the way it's usually written, the FeO Silica diagram, saturated in iron. So what you really imagine, this is somewhat similar to the previous diagram, but not exactly the same. Same idea. In this diagram, we're going to start with FeO and silica, and we're going to put it in equilibrium with Fe. Before we put it in equilibrium with oxygen, at a fixed oxygen activity of 0.21 atmospheres. Now we go the other way and we put it in equilibrium with iron. Okay, but now you can look at this, one way of looking at it would be, if the iron was in fact pure iron, I could do it the same way. What I just showed you here is you could consider that you have it's an equilibrium with, okay, so this is what happens if you fix the oxygen pressure. Geometrically, you're tracing along this line and projecting it onto that line. You could consider what you're doing now is you've got oxygen, Fe and silicon. Over here I have SiO2. Here I have FeO. And what I'm doing is I'm taking a line of constant iron activity. Okay, so I'm going along, this is before I went along a line of constant oxygen activity. Now I'd be going along a line of, say, constant iron activity. So this is the activity of iron equals 1. That's the line along when it's in equilibrium with iron. So now I would have tie lines lying along here, and I could project through the iron corner. Same sort of idea, except I'm projecting through this corner now rather than through that corner. Okay. The trouble with that, of course, is that that's fine, and in this particular case it's pretty close to the truth. Because the iron phase, if you actually set this thing up, if you had your high temperature slag, your oxide phase is in equilibrium with the metal phase, the thing is now going to be at equilibrium. So you're going to have down here, you're going to have iron, and up here you're going to have your FeO, silica, plus iron, Fe2O3, whatever phase, your slag phase. If the iron is pure iron at equilibrium, then that's the same thing. It's exactly analogous to fixing PO2, except for fixing this other component's activity. Okay, but in reality, the iron is going to contain a little bit of silicon when the thing's reached equilibrium. Okay, so you're not really projecting this isn't really what you're doing in the real case. What you're really doing is you can't keep it in equilibrium with iron. You can't practically keep it in equilibrium with iron at one unit activity. You can only keep it in equilibrium with an iron silicon alloy, whose content of silicon is going to be determined by the exchange reaction between the phases. In the case of this particular system, this is very close to the case. The activity of iron is 1, but if I had, say, the iron zinc oxygen system, then this phase could actually contain more zinc than iron in many cases. Okay, so I can't really do this in actual fact. What I really have then, if I had iron zinc, okay, if this was iron zinc and this was zinc oxide or something, then I would have the slag phase up here would be in equilibrium with an alloy along here, so I'd have tie lines like this, and it's not. Okay, so that's your problem. So basically what I like to look at, so this diagram, anyway, the diagram still obeys the rules of binary phase diagram because you're on a line at which everything, two phases in equilibrium. Generally, when you see this diagram written, when you see this diagram drawn in a textbook, first of all, you never see the iron. You see this phase would be monoxide plus Fe2SiO4. You don't see the iron written, but I put this in here to every phase field here. I've put in iron to indicate that really the iron is there. It's not an oxide diagram, it's a diagram with iron. The iron is present. And again, this is really necessary if you're going to look at this. If you had iron, zinc, oxygen, then you definitely have to have the metal phase here because it's a variable composition. Also, these horizontal lines generally are not plotted. They're simply the place where the iron changes phase. Okay, from alpha to gamma to delta to liquid. So generally you'll see this diagram in a book of oxide diagrams. It won't have those horizontal lines on it, and you don't see iron listed anywhere. And in the case of something like the iron silicon oxygen diagram, that's sort of okay because you can look at it as an equilibrium with pure iron. But when you're dealing with anything less reactive than silica, like iron zinc oxygen diagram, then this diagram is totally different, and you have to put in the metal phase has to be in here, the composition has to be given. You've got to indicate the whole thing. Why did that happen? Why is it doing that? There. What happened to it? Yeah.
No, it's
It is okay?
Shut right now. I didn't touch it. I won't do it. All plugged in, this is on. Okay. Nothing seems to want to do anything. Anybody got any ideas?
It seems that you have your battery is
Yeah.
down and
It will take some time.
Why is the battery down? It's still running.
oh, yeah, okay.
Well, the screen is still working.
Well, no, but the lights are on down here, and that just does. So that would seem to indicate that the plug's in. But it never gave any warning. Usually it says your battery's getting low.
And on your there is a blue light or a light on your
A little blue light here that looks like it's a plug. And that looks like it means a battery. But everything's plugged in. Yeah, well, see if every jock has an idea. It looks to me like it's a plug. Looks like a battery. Something just happened? More lights came on.
or something.
I'm not getting any screen on here.
Allez, deuxième.
You
Start menu, là, on dit. Avec les flèches.
quelle flash?
Les flèches sur le clavier.
No.
Un truc.
Ça?
Non, le deuxième. Start menu, c'est mieux.
It's more difficult.
Rien dans l'écran, rien.
Vous voyez pas l'écran? Ah non, mais là, c'est juste...
Il a fait ça.
il va peut-être revenir. Peut-être.
C'est juste
Sinon, c'est...
à côté et tout. Ah,
il y a
ok.
rien, là.
Ça revient. C'était le problème.
Je sais pas.
Hmm.
Il va démarrer, il va...
There you go. Must have run out of juice or something. All right, well. Okay, so we're back, I guess. Okay, so generally this diagram, as I said, is often called the FeO SiO2 diagram at iron saturation. So the best way, however, though, as I said, is that in the general case, you can't consider it to be in equilibrium with pure iron. It's in equilibrium with an iron silicon alloy, which is not going to be a good approximation if, in fact, you have something like zinc. So the way I like to think of this diagram, or the way I calculate this diagram with FactSage, okay, is I consider it to be an isopleth, FeO SiO2. And what you're going to have is you're going to have oxide phases which lie pretty well on that line in equilibrium with the metallic phase down here. You can be in a two-phase region between phases that exist on the oxide phases, and then you can have a metallic phase. In the iron silicon system, the metallic phase is all basically pure iron, but you could have what I like to look at it then is calculated as an isoplethal section. In other words, like the first diagram, the Fe3O4 SiO2, you make an FeO SiO2 plus a little bit of extra iron, so that you're actually calculating a slice very, very close to the FeO Silica diagram. So you're getting a vertical section, which is just a little bit on the metal side of the FeO SiO2 diagram, in order to assure that you've always got a metal phase present. They put just enough, so you're really what you've got is you can imagine that you have here, you have your oxide phases, your FeO Silica, your oxide phases, and down here you have a metal phase. The metal phase is a very small amount. Okay, so basically your composition is giving you the composition of this phase in equilibrium with a very small amount of metal, okay, to assure equilibrium with the metallic phase. And then you're going to get the thing right, and that is the safest way to do these. So I define it as temperature, the components are FeO Silica and iron. Okay, and so the size is FeO plus silica. These are the variables, with the number of moles of iron over the number of moles of FeO plus silica to be very, very small. That is, the components of the system have been defined as FeO Silica and I made a mistake here, this should say iron. So we define the components as FeO Silica and iron with a sufficient excess of iron, with a just sufficient excess of iron, so there's always get a metallic phase at equilibrium. And then, if you end up with something other than and then you can look then when you do the calculation with equilib or with phase diagram, you can look and see what the composition of the metallic phase is and see what's really there at equilibrium. Now, of course, if you really want your hypothetical diagram at constant unit iron activity, I mean, you could still have a diagram, oxygen, iron, zinc, in equilibrium with pure iron at unit activity. And you could calculate the diagram theoretically just the way we did the other one, fix the activity of iron equal to 1. Okay, but then that would be something that would be very hard to realize in a practical experiment. How are you going to keep, you could keep your oxide phases in equilibrium with a PO2, atmosphere of constant activity of oxygen, but how do you keep it in equilibrium with a metallic phase with the activity of iron equal to 1? You can't really do that unless you have iron vapor or something. So that doesn't correspond to a real situation. The real situation is you're somewhere here. In fact, in a real slag, you might have a very large amount of metal. In a real situation, you might consider the total amount of FeO Silica, iron, and silicon in your system, and take the actual section across, isoplethal section across the whole diagram, and then the diagram would give you the oxide phases and the metal phases of equilibrium. Okay, so you can see that interpretation of oxide diagrams, you got to be careful. I'm going to skip section 7.9, but you might find that interesting. And I'm going to go on to figure 7.10, which I think you should find useful for the work you're doing. Phase diagrams of reciprocal systems. So we consider figure 47, and this is the system sodium chloride, calcium fluoride, calcium fluoride. This is called a reciprocal salt system. It's called a ternary reciprocal salt system, and by definition a reciprocal salt system is one consisting of 2 or more cations and 2 or more anions. If you have just one cation, like sodium chloride, potassium chloride, rubidium chloride, cesium chloride, that's not reciprocal because you've only got one cation. You have 2 or more cations and 2 or more anions. In this case, you have 2 of each. Okay, now since excess sodium, calcium, fluorine, and chlorine are virtually insoluble in the ionic salts, that is sodium chloride, all these salts are almost stoichiometric. Yes, you can have a little excess of sodium or chlorine and sodium chloride, but the amount is really less than parts per million. It's extremely small. So they're virtually insoluble. So this is very close to a quasi-ternary system. In actual fact, it's a quaternary system. You have sodium, calcium, fluorine, and chlorine. But in actual fact, it's a quasi-ternary system in which the number of moles of fluorine plus chlorine, this is charge balance. Okay? The number of charges on the cations have to equal the charges on the anions. Okay, so you're taking a section, you're taking the quaternary system in a tetrahedron, and you're taking a section across in a plane across it in which this is true. Okay? And all tie lines basically lie in that plane. Okay, imagine a tetrahedron, sodium, potassium. I'm going to try to draw this. I'm a horrible artist. But you imagine that you have a tetrahedron, and at the corners of the tetrahedron you would have sodium, calcium, fluorine, and chlorine. Then you imagine you would have the calcium fluoride is somewhere here, calcium chloride is somewhere here, sodium chloride is here, sodium fluoride is here. So This is a plane. Okay, and now, so your reciprocal system is between the compositions of the salts, and all phases, solid and liquid, all have compositions on that plane. Nothing is outside that plane. So it's a quasi-ternary system in the sense that your composition variables have one restriction on them. You can't fix all four number of moles. The composition variables have a restriction on it. Okay, or the other way of looking at it is in that plane, all compositions, to give you any compositions in that plane, you only need two composition variables. Okay, and this is, okay, the compositions of all phases lie in the plane of the diagram, and the lever rule applies, so we go to figure 47. And there we have figure 47, and the way this is plotted then is, okay, this is a constant temperature section. So what we have here then is we have, this is how these things are usually plotted. Okay, this is the corners of the diagram, this is the composition square, is the most convenient way to plot this, and this is this square here with the salts at the corner. So each corner of the diagram represents the pure salt. Each axis of the diagram, each side of the diagram represents a binary system. So this is the sodium chloride, calcium chloride binary system. This is the sodium chloride binary system, and so on. So if you were to draw a vertical section here versus temperature, this edge of the diagram would be the NaCl-CaCl two-phase diagram. If you were to draw this thing with like a square prism with the temperature going up, each face is going to be the binary phase diagram. Okay, and this obeys all the rules of ternary phase diagrams. You have two-phase regions and a two-phase, this is a one-phase region here for pure liquid is in this region. It's full, everything, you see that the four lines come together, the nodes, these are all zero phase fraction lines. It's a standard section with three-phase triangles, two phases with tie lines. The lever rule applies and everything because all phases are in that system. Okay. It's very much like a ternary isothermal section. It's just plotted differently. Now, what I plotted here is the molar ratio of fluorine over fluorine plus chlorine. So the vertical axis is the anion ratio. So along lines, horizontal lines, you're starting here. You have chlorine and no fluorine, and then you're changing the fluorine-chlorine ratio. Along here, we're changing the calcium-sodium ratio. But rather than plotting it as, say, here I plotted fluorine over fluorine plus chlorine. Here I plotted 2 calcium over 2 calcium plus sodium. This is called the equivalent fraction. This is like a molar ratio. This is well, the molar ratio this way, but you sometimes call this an equivalent fraction because calcium, you weight each number of moles by the charge. Okay, so calcium has twice the charge of sodium, so this is 2 times the number of moles of calcium over 2 times the number of moles of calcium plus the number of moles of sodium. Okay. Let me show you why. You don't have to do that, but I'll show you why that's the way it's generally done, is because if you don't do it that way, you don't get straight tie lines, and the diagram doesn't look very good. So to explain this, what we do is this. So we consider, okay, formally to understand that system, we consider the components to be the elements, sodium, calcium, fluorine, and chlorine. I chose temperature, pressure, and the 4 mole numbers. And the size of the system is defined as the number of moles of fluorine plus the number of moles of chlorine, which is equal to necessarily twice the number of moles of calcium plus the number of moles of sodium. Okay, those two are equal, correct, by charge balance. Okay, the phase diagram variables then are temperature, pressure, fluorine over fluorine plus chlorine, and 2 sodium, 2 NaCl over that, or that, because this then has to equal 1. Okay. And you see here of this ratio here, the denominator here is N fluorine plus chlorine. Here the denominator is 2N calcium plus N sodium, but they're the same thing. They have the same denominator. Okay, so that's how we choose. That's what the diagram is. So the diagram is temperature, pressure, and this ratio constant equals to 1, and it's the anionic fraction versus the cationic equivalent fraction. And then you end up getting a proper phase diagram because it obeys the rules. The variable axes are called equivalent fractions, in which the number of moles of each ion is weighted by its absolute charge. Now, as I said, note that if sodium if sodium, calcium, fluorine, or chlorine were actually significantly soluble in the plots, in the salts. If you actually had a molten salt system in which the salts were not exactly on this plane, you could still plot the diagram that way, but then it would truly be an isopleth. The tie lines wouldn't lie in the plane. You would have overall compositions in the plane, but the tie lines could pass through it. The diagram would then look a bit different, but you could still plot it. But generally, we consider that it's... Now, why do we do it that way? Why don't we? So figure 47 could be drawn. There's no reason you can't. Could be drawn with the axis variables chosen as simply the vertical axis could be the anion ratio, and the horizontal axis could be the cation ratio without any weighting factors. Okay, and in that case, you would end up with a phase diagram which looked the same. However, I can show what, I won't be bothered, but you can look it up if you want. It would be a valid phase diagram. It obeys all the geometrical rules. However, the tie lines in two-phase regions would no longer be straight lines. Okay. And it's kind of interesting, and you can kind of work this out yourself. What you want, just go to the diagram. If you look at the diagram, okay, in this diagram, you're in a two-phase tie line. This is plotted correctly, and so tie lines are straight lines. So if I'm joining two, where's it good? Okay, well here, let's take liquid plus NaF. Okay, and here your tie lines go from NaF to the liquid, NaF to the liquid, NaF to the liquid. Okay, so I would have a tie line coming along like this. It's a straight line. So an overall composition here, I have this end of the tie line in equilibrium with that end of the tie line. If I were to plot this as, let's take the 2's out of here, the diagram would have the same geometry, but it would be a bit distorted clearly because I'm changing the axis. And now I would have a tie line. I would have sodium fluoride in the two-phase region as an equilibrium with the liquid. But that tie line is not a straight line. In other words, the compositions in which sodium fluoride in equilibrium with the liquid do not lie on that straight line, they lie on a curved line. A straight line drawn between the compositions of the two phases in equilibrium does not pass through the overall composition of the system. Okay, and that makes the diagram not so nice to interpret. Okay, so it's generally done this way. You can figure that out yourself if you want. That's why we do it this way. Otherwise your tie lines are curved. Or if you wanted to know if this were plotted as mole fraction without the 2's, and you had an overall composition here, you couldn't, just looking at the diagram, draw the tie line because you wouldn't know how to draw it. You'd have to have all, I could take the diagram and I could draw all tie lines on the diagram, but okay, they're not straight lines. And so basically on any phase diagram section you can show it. I don't prove it in the paper, I give you a reference for it. Any phase diagram section, not just reciprocal salts, but any diagram, ternary, triangle, whatever. If you're drawing any phase diagram, when you're plotting two composition variables like this, the denominators of each variable should be the same. If they're the same, then you get straight tie lines. If they're not the same, then you don't get straight tie lines. Here the denominator, 2 calcium plus sodium, is the same as fluorine plus fluorine. Okay, so that assures you have the same denominator. So we do this in FactSage when you're using the phase diagram program. You will see that if you're choosing composition variables, all the composition variables have to have the same denominator. And we do that simply to ensure that you're going to get diagrams with straight tie lines. Otherwise, you can get a diagram without straight tie lines and not realize it. So that's what that's all about. Now, this diagram, you'll often see it sometimes plotted as follows. In fact, you probably will see this is the same diagram. I like to plot it this way with sodium chloride, sodium, and so on. But it will be written this way as 2 sodium chloride. Here you write 2 sodium fluoride. Over here you have calcium fluoride and calcium chloride. That is, you define your components such that you have the same number of charges in each one. Okay, and if you draw it this way, then this axis would be the number of fluorines over the number of fluorines plus the number of chlorines. And this I always get confused when I look at it this way. But this would be, it looks like it should be the other way, but it really is that way. This is the same thing as that. They usually draw it this way. I don't know. Yeah, right, okay. So this axis could then be the number of moles of calcium chloride. This is how they look at it. I like this way better. But the number of moles of calcium chloride over the number of moles of calcium chloride plus the number of moles of 2NaCl. Now the number of moles of 2NaCl is 1/2 the number of moles of sodium. Okay. I have a mole of 2NaCl. I have the number of moles of 2NaCl. If I have 2 moles of NaCl, that contains 2 moles of sodium. Okay, so the number of moles of NaCl is 1/2 the number of moles of sodium. So this could be the number of moles of calcium is the same as the number of moles of calcium chloride. The number of moles of 2-sodium chloride is 1/2 the number of moles of sodium. So let's put the 2's up here and we end up with the same thing. Kind of weird. But you'll often see it drawn this way in phase diagram books. They put the corners this way. This is to indicate, to make it clear, I suppose, that they're using these equivalent fractions. If you define your components as always containing the same number of equivalents, that is the same number of charges, this contains 2 positive and 2 negative charges, this contains 2 positive and 2 negative charges. That's another way of looking at it, or this is the way of looking at it. It comes up to be the same thing. The reason, and you'll see it defined differently, but the reason that the only reason that we put these equivalent fractions and multiply it by the charges has nothing to do with the fact really that it's a charged system. It has simply to do with the fact that no matter how you do it, even if this wasn't a quasi-ternary section, even if sodium, fluorine, and that were soluble, you would still want to do it this way so that you get tie lines that at least are halfway reasonably straight. So, okay, it just has to do with the fact that geometrically you need the same denominator here as you do up here if you want the diagram to look properly. So there's your reciprocal salt phase diagrams, which you're going to come across for sure. And I talk about this as, this is called a reciprocal ternary system. It's a reciprocal salt system because it has 2 cations, 2 anions, more than 2 or more. And it's ternary because it has exactly 2 of each. So ternary system requires 2 composition variables. So it has 2 composition variables. Although it's really a quasi-ternary phase diagram. You can have reciprocal quaternary systems. You could have 3 cations, sodium, potassium, and lithium, and fluorine and chlorine. That would be a reciprocal quaternary system, and so on. And this is actually how you have to set this up. If you're going to calculate this diagram with FactSage, this is the way you're going to have to set it up. You're going to have, if you try to use FactSage and you try to define your components as NaCl, NaF, calcium fluoride, and calcium chloride, you're going to get in real trouble. I don't know if you can really, well, you can do it, but it's going to be a real bugger, because then you're really defining as a quaternary system, and then you're going to have to define somehow you're going to get the plane. The best way to do it, the simplest way to do it in FactSage is if you want to calculate that diagram in FactSage, which is what I did, I did it exactly this way. On the first window, these are my components: sodium, calcium, fluorine, and chlorine. Okay, I set this up as I set up 3 composition variables. This is one, this is the second, and the third composition variable is this ratio, which I set to be constant. And then the whole thing works. Okay. As I said, FactSage will not let you choose anything other than this, because you have to have the same denominator. So try calculating the diagram with FactSage. Okay, FactSage will not, the phase diagram program will not permit you to have anything other than the same denominator in all composition variables, so that you only get straight time. And that's discussed in section 711. And I'm not going to go through 712. 712 does the enthalpy diagrams formally correctly. And just to be complete, I've talked only about sections. I'm not talking about projections particularly. There is, however, about rules of construction. I'm not talking about rules of construction of projections, but if you want to just take a quick look at figure 27, which is somewhere. Okay, figure 27 is a projection of a liquid to surface. A ternary liquid is projection, which you've all seen. And there is a rule of extensions too, is that when you have, these are your univariate valleys, you all know what I'm talking about, I hope. If you don't, you better read about it. These are your univariate lines coming in here. And at any place where three univariate lines come together, be it a eutectic or a ternary peritectic or whatever, you have extension rules which are shown by the dotted lines. It's sort of similar to the PT diagram, is that this line, this univariate valley has to extend into this region. This univariate valley has to extend into this region. You need a, okay, if you have three univariate lines coming this, then these must extend into the opposite region. That can be proven, too difficult. I don't do it in the book here, in the chapter here. So if you actually see a diagram in which that doesn't occur, then the diagram's wrong, thermodynamically incorrect. Naturally, when you calculate it with FactSage, you don't have that error because FactSage calculates the diagram from thermodynamics. Actually, you can calculate, as you know now, or as you should know, you can calculate polythermal projections using FactSage. Okay, and FactSage, well, first of all, FactSage, this was calculated with FactSage. It puts on the isothermal lines. Of course, each isothermal line is just an isothermal section. But the univariate valleys, it actually, you'll see it calculating the univariate valleys. And the univariate valleys are a second calculation, which is actually a double zero phase fraction line. Remember, you go along a zero phase fraction line, you keep the amount of one phase just equal to zero, in equilibrium with other phases. Now you change the temperature, and as you change the temperature, you keep yourself right on the line at which you have, say, a liquid phase in equilibrium with zero amount of each solid phase. This is the composition of the liquid in equilibrium with the two solid phases. So if you have a liquid exactly on that point, then it's in equilibrium with the two solid phases at zero amount. Okay, so you then follow it as you go down in temperature. You do like a double. As you follow a zero phase fraction line, you're doing a double zero phase fraction line, keeping the amount of both solids exactly zero as you move along. So it's the same sort of principle. So with FactSage, you can, if you ask for a polythermal projection, it asks you two things. Do you want the isothermal lines and do you want the univariate lines? Those are two separate calculations. Sometimes the univariate line calculation can take a long time. And sometimes you can decide where you don't really need it. You just want a whole bunch of isotherms, and you can see where the isotherms come together, define the univariate line. You can draw it in yourself if you're in a hurry. So, the calculation. Okay, that is a little extension, which I've never actually seen anywhere mentioned in any books, but I can prove that. Okay, let's take a break. And I think we've probably lost the whole thing there again. Well, since it stopped, I doubt if, in fact, it isn't even on here, if you notice.